So this we need to determine the generation equations for generations. So P1 is equal to 1 minus B1 by lambda minus 2 B1 to B2 by A1 by lambda plus 2 B1. This is the expression which we do have for P1. So I'm trying to simplify this expression now. 1 minus B1 is 16 by lambda is 35 minus 2 into B12 is minus 0.0012. P2, I'll keep it like that itself. And this is 0.03 by 35 plus 2 into 0.005. Yep. So now if I do the LCM, this is 35 minus 16 plus 35 into 0.0004 into P2 by this is 0.03 plus 0.35. So this will be somewhere around. So let me calculate first. So this is going to be 50 plus 0.2211. So this is a expression. So I'm taking this one P1 now as I'm erasing all these things. So P1 is going to be 50 plus 0.2211. So this is my expression for P1. Now similarly for P2, P2 is equal to 1 minus, this is must be B2, this is 12 minus 2 B21, this will be P1, this will become A1, this is sorry A2, 0.05, and this is B22, it is 0.02. So 1 minus B2 by lambda minus 2 B21 P1, A2 by lambda plus 2 B22. So this is the expression. So now, what are the changes which I do have now? Yeah, this is the expression. So simplifying this one now. This is 0.19. This is 35 minus 12, it is 23. So what I'll be getting here, P2 is equal to, so what is P2 now? It is 23 by 9.9. It is 121.05 plus 0.4421. So these are expressions for P1 and P2, which we need for optimizing the things. So now let's get back to the things. The third step is about optimizing P1 and P2. Initial values of P1 and P2, I do already have them as 633.33 and 460. So now revised value of P1, I will employ this equation. So I do need P2 now. So if I substitute P2 here, so let's see what is the value which I'm going to use. Okay. So the value is going to be 460 into 0.2211 plus 50. So its value is 151.7. 151.7. So now P2 value, I will employ this latest value of P1 here. So this value is going to be 151.7 into 0.4421 plus 121.0. So its value is 188.1. See, there is a huge difference. Again, I am applying this value for getting P1. So again, this is 181.11 into 0.2211 plus 50. So now the value is 90.0. 90.0. Now again employing 90.04 now. So its value is 160.8. Still there is a huge difference between the subsequent iterations. So again I am gonna go for that one. So normally it takes 5 to 6 iterations for getting a convergence. This is 85.56. So slowly we are getting into convergence. Till now, so its value is 158.87. So we are getting slow convergence now. So we'll go with the fifth one. I hope I will be getting a convergence now. 158.87 into 0.2211 plus 50. It is 85.1. See, finally I have got a convergence now. It is closer. So these, I think further if you do it again for the sixth iteration, I think they will be very close. So I am stopping it here. So I have got, I am assuming that these are my final values of P1 and P. So my fourth step is computing here. As already been said, it is going to be so what is my P1? It is 0.005 into B1 is 85.12 square plus 2 into B12 is minus 0.002 into B1 B2 is 85.18 158.68 plus B22 is 0.002 into 158.66 square. So now let's calculate this value now. It will take for me 1 minute of time. So let's start. B22 is 0.002 is the value. This is the correct one. So now, after obtaining the value of PL, now our final thing is delta P. Delta P is summation of the generations minus demand plus losses. So what is the summation of the two generations of 85.12 plus 158.68 minus demand was 200 and the losses are 54.169. 54.169. So this is the way how we will be computing delta P. So let's see what is the value of this one. So now I have got a little bit lower value and compared to the previous one, it is somewhere around minus 10.36. Minus 10.3693 meters. But still, it is not closer to 0. I feel that it is somewhat a larger value than compared to 0. So, I will again change my lambda. Since I have got delta P as negative, I will be increasing my lambda again. So, this time, increase lambda to, let us suppose I will increase it to 35 is the initial value. So, I will increase to 37.5 now. Or I will go with the 37. Okay. I will go with 37. Let's see what will happen if I go with 37 now. So I am changing this value to 37 now. So let's look back again. If I change to 37, my P1 value will be 37 minus 16 by A1. So 37 minus 16 is, I think it is 21. So 21 divided by 0.03. So it is going to be, my P1 initial value is going to be 700 megabytes. Here it is 37 minus 12 by 0.05. So 37 minus 12 is 25 divided by 0.0. It is 500. This is going to be 500. So now I have got the initial values of P1 and P2. Now what I should do? I should go with optimizing these things, right? Optimizing P1 and P2. So before optimizing for P1 and P2, what I should do? I must fit my expression for P1 and P2. So what is P1 expression? 1 minus V1 by lambda. It is 16 by 37 minus 2 into V1. 2 is minus 0.0012. P2 by A1. A1 is 0.03 by lambda plus 2 into V1. 0.05. I'll take 37 as a LCM. 37 minus 16 is going to be 21 plus 0.0037 into 5. So this is 0.4. Let's look back to this equation now. 1 divided by 0. So it is going to be 52.5 plus 0.2. So I am writing down here the expression 52.5 plus 0.3. Similarly, now let's get back to the equation number P2. It is 1 minus V2 by lambda 12 by 37 minus minus 2 into 0.0012. This is P1. A1 by lambda, it is A2 by lambda. 0.19. So, following this one, what will we get? Let's see. 25 by 26.26 plus 0.4485 T. So these are the expressions for P1 and P2 for us. Now, we do have the initial values of P1 and P2 as 700 and 500. We need to optimize these two with the help of these two equations. Now, let's see what is the optimization of these two equations. The first one is I'm going to substitute 500 here. If I substitute 500 here, my value will be 163 points. Now, this is 440.1. Again, I'm going to substitute this one 440.1 into 1 I think there was a mistake here. This is 62.5. This is 199 actually. This is 199.8. 199.5. I think now we can get a quick conversion. 199.5 into 0.222. This is 96.7. these are converged values now. P1 and P2. I hope it's enough for us. Now we will calculate PL now. PL1 is B11 P1 square plus 2 B12 P1 P2 plus. So B11, B12, B22 values we do have. P1 and P2. I am taking these values. Now let's see what our final values will be. It's 59.68 now. So delta P is summation of generations minus demand and losses. So summation of generations, the summation of these two. So let's see what is P1 plus P2. 66.4 plus 89.5 minus the demand 200 minus losses of 9.68. So it is minus 3.78. Minus. So we are getting closer to the value. But since it is not closer to 0, if you want, you can end this one and you can treat it as P1 and P2 or the final values. You can take it as a final solution. But if you want to have a still perfect value, then since it is negative, you can replace delta because you do have 27. Now you have got a little bit closer for this one. So to replace delta with 37, so you can go with 37.5 or 37.6 so that you will be getting it closer to some minus 1 or 0. So this is the way of doing this problem. Maybe it takes a lot of time, but once you practice it for 2 or more problems, then it will be easier for you. It is not going to take much of your time. So I'm closing it this one to approximately minus 3.78 megahertz. I'm feeling that this is okay for me. So I'm taking the final generations as 89.5 and 166.4. Okay. So these are my solution here. ELD with losses. Losses are coordinated because I'm employing coordination equations. So what are P1 and P2? P1 is 89.5 megahertz and P2 is 166.4 megahertz. Okay. So these are losses being coordinated. Now we will see the last case of the ELD problems where we should include the losses, but we should not coordinate. Now case B, ELD including losses, but not coordinated. If losses are to be included but not coordinated, the condition is IC must be equal to constant. This is the condition. This was the condition for ELD with losses, isn't it? But the constraint, this is condition for ELD without losses. Or what we call it as coordination equation without losses. This is coordination equation which does not include losses. Okay? But constraint you are supposed to include. See, This is the coordination equation. The condition is basically called as a coordination equation. In coordination equation, I am not employing losses. Okay. In coordination equation, I have not employed losses. But whereas in constraint, I am including losses. This is the concept. ELD including losses in the constraint, but not in the coordination equation. This is coordination. And this is constraint. Losses are included in the constraint, but not included in the coordination equation. If not included in the coordination equation, then it is very, very simple. Now we will see for this one. Which means IC1 is equal to IC2, isn't it? What is IC1 and is equal to IC2? A1 PG1 plus B2. This is the IC1 for IC for the first plant. For the second plant, it is, see what is this equation? 0.03 P1 plus 16 is equal to 0.05 P2 plus 2. This is the equation. This is the condition. Second one, constraints. Constraint says that sum of generations P1 plus P2 must be equal to U demand, which is 200 constant term, plus losses. Losses, we do have the equation. What was the equation for us? B11 P1 square plus 2 B12 P2 P1 P2 plus B22 P2. So I am including this equation, but I am not considering this PL in coordination equation. This is the coordination equation. This is the constraint. So I am simplifying the constraint. If you carefully see, P1 plus P2 is equal to 200 plus B11 is 0.005 P1 square minus plus 0.002. This is equation number 2. Solving 1 and 2, we will be getting P1 and P2 values. Now we will try to do that. See in this one. From equation 1. From equation 1, can anybody say what is P2? P2 is equal to 0.03 P1 plus 16 minus 2 by 0.0. This is which means that it is going to be 3 P1 plus 400 plus 5. It's 0.6 P1 plus 8. So this is equation number 3, which I have obtained from equation number 1. Now I will substitute equation 3. In equation in here. So this is P1, 0.6 P1 plus 80 plus is equal to 200 plus minus 0.0024 P1 So now this entire equation is in P1. It is a quadratic expression. You solve what? You solve for P1. So let's solve for P1 now. We'll try to solve this for P1. Let's see what we'll do. Yeah. How many square terms are there? There is only one square term. 0.5 P1 square. I'm writing this entire in the right hand side. First, I will be choosing the P1 square terms. 0.005. Here also there will be a P square term minus 0.0. We'll try to solve this equation. But if you solve this one, you will be getting the values of P1 and P2. So these are the economic load dispatch, including losses but not called. I hope you will solve this problem. If I do find time, then I'll be solving it next class. Okay. So thank you guys for joining. I hope you have understood how to solve these problems. case 1, which we have discussed earlier, which was ELD without losses. Next was ELD including losses and quality. Okay? Now this one, the last one is ELD with including losses but not quality. Just we are employing the two equations. In condition, we are not employing here. Whereas in constraints, I am employing here. Thank you for joining.